Okay, now we have 43 participants, 43 students, 44. Okay, this session has been recorded. Okay, it's going to be recorded. Okay, before we start our session, I would like to recap what we have learned the last class. Anyone? What have you learned from the last class? You can comment over there. What have you learned from the last class?
Meter. Manometer.
Yes, manometer.
The chat has been disabled for me.
How to calculate the tank?
How to calculate?
The pressure at point and how can we section it?
Okay, correct. So first we learn about the pressure measurement device. That consists of two, which is barometer that measure the atmospheric pressure using the mercury. Why mercury is used as the fluid medium to measure inside the barometer? Anyone?
Because of its low density and low vapor pressure. High density and low vapor pressure.
Compared to Pascal, right?
Okay, yes, compared to Pascal. Why mercury is used for the fluid medium?
Low evaporation.
Low vapor pressure, correct. And second one?
Low density.
The density.
Okay, high density. That means low volume. All right. So when it is low volume, that means the device can be designed as compact as possible. Right. So for today's session, all right, let me open back the course information. Can you see this course information? So we are in the weeks of 3. All right. So this week we supposed to learn the fluid at rest, which we have covered the last week. All right. That means we are advanced now. And today, I'm going to cover the forces on plane area. All right. So this is gonna take this week, complete this week, because this quite tough because it involves of derivations and technical knowledge as well. All right. So for this lecture, I'm going to cover this part, which is forces on plane area. All right. So forces on plane area. So what do you think, or what do you know of forces on the plane area? Anyone? What do you think? What's your predictions of force on the plane area? What would it be? What would it be?
Hello?
Yes.
On plane areas, the force all over there is constant. I mean, because it's plane, so no variation of forces.
Okay. Which direction constant?
Like on the x, if it's on the x direction.
Yes, correct. In the x direction, all the forces are the same. How about the vertical direction?
It changes with elevation, of course, as we are studying about in liquid. It has to change with elevation.
Yes, as you can see from the previous derivation of the hydrodynamic equation, which is delta P is equal to negative gamma delta Z. That means the change of variation, the change of elevation will have change in pressure. All right. So as you can see, now we cover the force on the plane. That means we have a water all right, and then we dip a plane, all right, we dip the object considered as the plane, all right. So for this case, the fluid still at rest, no tangential shear forces, normal force exists, all right, and have normal stress, which is pressure. All right, I think this is covered already. I have explained previously, when the fluid at rest, no tangential forces, which is the force acting parallel to the surface. There is no motion. Because there is no motion, the force, no tangential forces. All right, only the normal forces exist. All right, the normal stress, which is perpendicular to the surface, we call as the pressure. All right, if surface is present, right, all forces are normal to the surface. For example, this is, all right, I hope you can see, this is the plane. When we dip this plane into the water, we have the forces. All right, all the forces acting perpendicular to this plane. So, for example, this is the vertical plane, and then the force will act in this direction, perpendicular to this surface. All right. So, if pressure is uniform, distributed over an area, so that means all this vertical plane dip into the water, the pressure is uniform, distributed over an area, force equal pressure time area. I believe you know already the force. So what is the formula of the pressure related to the force and area?
P equals to F over A.
Okay, correct. Good. Okay. So all right, let me open this. All right, so we know already pressure is equal to force over area. So this is the basic of the force inside the water. All right, this is force, this is pressure, this is the area. All right, in order to get the force, pressure must multiply with the area. This is what it means. The force is equal to pressure times area. All right. Magnitude of the resultant force. Okay, this is quite tricky. The magnitude, that means the value of the resultant force. What is resultant force? Resultant force is the total force. All right. Is located at, is at the area centroid location. All right. I will explain later on for this case, but I need you to take note on this. And number 3, pressure is uniform for submerged horizontal area. All right. For example, we have the vertical plane. The forces will have the uniform distribution. What mean uniform distribution? Will have the same length. Okay, the same length, that means the same magnitude. For example, this is 30 Newton. This is also 30 Newton, 30 Newton. That is what it means. All right. The pressure is uniform for submerged horizontal area. So there are two fluid. Normally we use gases and liquid. For the gases, pressure variation in vertical direction is very, very small. All right. So the change of pressure for the gas from this point, point A, let's say, to point B, is very, very small because it is the gas. The gas, for example, like the air, okay, having very, very small density as well as the specific gravity, as well as the gamma specific weight. That is why normally when we involve the elevation for the gas, we normally omit it. you can calculate, but the value is very, very small. However, for the liquid section or liquid part, you need to have a further analysis because the liquid have very big of gamma specific weight as well as density. So it will affect the pressure because why? Pressure is directly related to rho, G and H or gamma and H. If the gamma and the rho is very high, that means the pressure is very high. So that is why the liquid you have to encounter when you deal with the pressure calculation. Alright. So this part can be seen from here. Can you see from the previous calculation of manometer? Can you see this one, manometer? Alright. Okay, this is manometer. So, for example, at this point, this is air. This is, for example, gas. Okay, and then this is the height. So normally, we just ignore this pressure because this pressure with this pressure around here almost the same. Because why? Because the density as well as the specific weight is very, very small compared to the density of the liquid. All right. For the case of gas, you can ignore the pressure of this elevation. However, if this is liquid, all right, for example, like oil, mercury, you have to consider because of having higher density as well as specific weight. All right, so far you understand what I mean, everyone? Okay, everyone. Are you okay, or are you taking your lunch?
Doctor, can you please repeat the last point?
Okay, what do you mean by the last point?
I mean the pressure in the pKgs, in the liquid and oil. I don't understand that point in the graph that you wrote.
Okay, okay, for this statement, the gases, the pressure variation in vertical direction is very, very small. Okay, because of why? Because of gamma and the density is very, very small. That is why when you deal with the manometer measurement, you measure the pressure level. For these cases, for example, this is gas, you can omit it. All right. If you deal with the liquid section, for example, this is liquid, and you need to consider this elevation. Okay, because why? Liquid have pressure equal to rho GH, has higher density. That will lead to the higher specific weight. Are you get it?
Yes, doctor, thank you.
Okay. All right, this is what it means. All right. So consider a vertical plane. All right, let's draw the vertical plane. So this is the most interesting part. Okay, this is the water. For example, this is water. Okay, this is water surface, or we call as a free surface. And then we dip vertical plane. All right, this is the vertical plane. All right, just imagine this is a very straight vertical plane. So what do you think of the pressure variations? Anyone would like to give your answer? What will be the pressure variation? What's it looks like?
It's increases.
Increases. All right. So the pressure at the pressure at the top. What is the pressure at the top surface? Equal to
Atmospheric.
for this case equal to 0. All right. We consider as the gauge measurement. Okay, so there is no pressure here, just 0, and then increasing with that will increase the pressure, right? So it will be like this. So from here, we can connect them together like this, the straight line. So this is actually the pressure variation, which is not uniform across the plane surface. All right. Just imagine this is the surface. All right. And then we dip into the water. This is the pressure variation. The more the depth, the more the pressure. It's very simple. All right. So from here, what is we have the resultant force due to the pressure. We call it as the pressure force. Where is the location of the resultant force? Anyone? Is it at the center of the area?
One third from the back of the triangle and 2/3 from the front.
Okay. Okay, normally that is correct. Yes, because you measure the centroid of the triangle, right? All right. So when we talk about the resultant force, let's say this is the centroid. I name here as the symbol here as centroid. Centroid. Centroid is the center of the area. For example, this is the plane. This is the centroid. Okay, this is L/2. This is L/2. The total is L. I hope you understand, everyone. Okay. So, for example, this is centroid. The resultant force is actually acting not at the centroid. All right. So, it is actually, can you see? Because of the pressure is not uniform, the centroid will be in this direction. All right. It is have a tendency towards the more forces. All right. So this is actually the resultant force. We call as the FR. All right, everyone. Do you get it? Do you understand? So far, everyone, are you there or are you?
Yes, understand.
Okay. So this is the resultant force. So from here we can. So from here we can name here from the surface into the centroid. We call as the H sub C. Subscript C, the height from the surface to the centroid, and from here, all right, this is centroid, and here is the P. We call as the center of pressure. So from here to here, we call as the H P. All right, the height from the surface of the water to the location of the resultant force. All right, please remember that. So far, do you have any question?
Doctor.
Okay.
Why did it shift the centroid more up? The centroid is almost the position where FR is there. Like that's where the centroid should have been. Like why did it shift the centroid more up? I mean, I don't get the point of shifting to the centroid point.
Can you speak slowly? I cannot.
I mean, why did you shift the point of the centroid? It should have been at the point of the resultant force, like mathematically.
Okay. You mean the centroid?
Yeah, it should have been at the FR point. Means mathematically it lies over there.
Okay, mathematically you need to understand the definition. As I mentioned, this is the area, not the prism, not the centroid of prism. Do you get it, Najmun? For example, this is the plane area. So what is the centroid? Where's the centroid? Here, right?
Center. Yeah.
Center. So the one that you said mathematically is this. this is yes as a centroid.
Yeah, I was talking about this. Yeah.
But now are we referring this or we refer this?
The second one, the triangle.
Which one?
The second one.
This one, right? So once we refer this, so the centroid is at this location. Okay, do you understand, Najmul?
Yeah,
you
yeah.
get it?
I got the point.
Okay, so we are not refer to the prism area. If we refer to the prism, yes, that is mathematically correct. But now I refer this as the area of the plane surface. Okay, so once deep at the middle section. Okay, so from here you know already the vertical plane where the resultant force acting on. All right. So consider second one. Consider the surface at an angle. All right. So for previous one, it is what's the angle here? Anyone? This is the surface and this is the plane. It is vertical 90 degree. All right. So what happened when we have the one surface at an angle, at arbitrary angle, at different angle? So let's say we draw here. Okay, this is the surface of the water. Okay, this is the surface of the water. And then we have the plane. This is the plane. All right. Just let's say this is the plane, yeah. In 3D, it will be like this. Okay, everyone, I hope you understand the 3D. But now I would like to draw in 2D only. Okay, this is 2D. Just imagine the width is into the pitch. All right. So from here, what do you think of the pressure distribution, anyone? What will be the pressure distribution? Okay. The pressure increase with
linear.
Okay. The pressure increase with depth. All right. So from previous one, this is the plane, and then the pressure acting in this way. All right. So for this case, it is the same thing. Okay. The pressure will increase with depth. Okay, anyone? Do you understand so far?
Yeah, doctor.
Okay, this is the pressure variation with depth. All right, remember our delta P, which is negative gamma delta Z. Increasing the Z, the more the Z, the deeper the Z, will increase the pressure. Can you see the pressure? This is the magnitude, the length. All right, so let's say we have a certain angle here. For example, we have theta, right? And for this case, where is the resultant force? Of course, the resultant force, okay. Let's say this is the centroid, all right? This is the centroid. The centroid at the middle of the area, all right? Because we consider as the plane. So where is the resultant force? Definitely, resultant force will be below the centroid, right? So this is we call as the FR, resultant force. Okay, so for this case, so from here, all right, from the centroid to the surface, what we call it here? Anyone?
Excuse me, doctor.
HC.
HC.
HC. from the surface to the centroid. This is HC. All right. Because of this HC, let's draw from this surface slanting to the centroid. So what is this? This is Y. This is YC. Everyone? Okay, this is YC from the surface to the centroid. All right. Okay, so from here, we call as the Y.
Why
YP.
if
YP. Yes. YP from here to here. Okay, this is YP. Okay. So this YP, let's say we have the change of Y from here to here. Okay, we have Y. Okay. Let's say we have Y. Okay, we have Y. Just arbitrary Y. That means the Y can have in any position. Maybe this position, and this position. So the Y is changing. All right. It is not fixed. The fixed is YC and YP. All right. So from here, from our basic equation, right? So from our basic equation, the pressure, which is, let's use this one. Okay, basic equation of pressure, which is pressure equal to force over area. Right, I believe you understand this. In order to get force, which is pressure times area. All right, so let's say we consider the change of force, dF will have the fixed pressure, dA. Okay, this is considered a differential. All right, from here, I translate into here. All right, the change of pressure, that means we consider very, very small surface area. dF equal to pressure times dA, the change of area. I believe you understand, yeah, this concept. This is the differential concept. All right, we know that the pressure, what's the formula of pressure other than this force over area?
Rho G,
Dx
Rho GH.
dV.
Rho G H, or simply gamma times H. Okay, so for this case, all right. Okay, all right. So for this case, can we see the H? All right, this is, can we relate H with the Y? Okay, this is H. How to get the in terms of Y?
Use angle.
Yes,
Trigonometry angle.
Trigo. So Y, this Y with the angle. Sine, cos, or tangent?
Sine.
Okay, let me draw here. This is Y, everyone.
Cosine.
And this is theta. Okay, this is this is H. The one I refer here, the H. So how to get the H? This hypotenuse Y, in order to get the H, Y?
Cos.
Cos will...
Sine.
Sine.
Sine theta. All right. So from here, replace the gamma with Y sine theta. So far you get it, everyone?
Yes, doctor.
Okay. So I try to substitute back this equation 1, this equation 2 into equation 1. All right. So from equation 1, which is dF Can you see dF equal to pressure? I try to substitute here pressure gamma y sine theta dA. Okay, which one? Okay, from here, I try to integrate because I want to get the solution. Okay, normally we do the integration to find the solution. So I integrate both sides. So what will be? Integration of with the differentiation will have
F.
yes, cancel. All right, for this case, which one is constant? Which is constant?
Gamma.
Gamma.
Y sine theta.
Okay, y is it y constant or not? Can we see the y always changing? Y changing. Y is not constant. So we need to have a constant outside. Which constant? Angle constant or not?
Yes.
Yes. So we move the constant outside and leave only y dA. Alright. So from here, once you try to integrate y dA, what will you get?
Volume.
Are you sure? Volume? Okay, basically, once you try to integrate this term, mathematically we have some kind of solution, which is integrations of y dA is actually equal to the first. Yes, it is YA. It is actually the first moments of area. All right. If you not sure, you can look at Google or internet. Once you do the integration of y dA, it is actually the same with the first moment of area, which is integration y dA will lead to this solution, which is YC time area. Right? So what is YC? That is the Y at the, anyone?
Centroid.
Yes, the Y at the centroid position, which is this one. Okay, so can I replace here with this one? Yes, I can replace. So force, resultant force, this is resultant force, is actually equal to gamma sine theta YC A. A is the total surface area. All right. So from here, can you see YC and sine theta? Can you simplify? What is YC sine theta represent?
HC.
Is it equal to HC or not?
Yes.
So we can say that HC is equal to YC sine theta. Okay, everyone? Do you get it? Do you understand?
Yes, Doctor.
Yes.
So FR is actually equal to gamma HC time area. All right. So we know already rho H is a pressure, right? Pressure equal to rho times H. So if this is subscript C, this is subscript C. So we can simplify further PCA. All right. So this is our equation that we going to use frequently. Okay, so far you guys understand the simple derivations?
Yes, doctor.
Yes, doctor.
Okay. So if you want to get the resultant force, just simply use this equation. Gamma HC time area, which is gamma of the water or other oil or fluid, times hc. hc is the centroid position to the surface and the area. It's very simple. Okay. So the center of pressure. Where is the center of pressure? Okay, this one. This is the P. The point P, the center of pressure. Consider a center of pressure points where the resultant force, all right, resultant pressure force acts on the submerged area. All right, so this is what I explained previously. This is pressure where the resultant force acting on the center of pressure P. So in order to calculate the location of center of pressure, we normally employ this method. Find the volume of submerged ship and line of action resultant pressure force pass through the center of volume. All right, this one is okay. Never mind. I will explain later on through the example. All right. So once we know, okay, let's say the force. What's the quantity of force? Is it the scalar or vector? Everyone?
Vector.
Vector.
Okay, so vector consists of
Magnitude and direction.
magnitude and direction. Previously, we discovered magnitude or direction? This equation, the magnitude. So where is the direction? The direction that we're going to discover now. Right? So this is the coordinate. The coordinate means the direction. Where is the location of the P? All right? To find the center of pressure, we're going to use this equation. All right? This is very simple. I don't want to show you very complex derivation. Just showing you this concept Y, CP. This is center, all right? This is centroid to the pressure point, CP, equal to negative I XX. This is second moment of area, multiply with sine theta over HC time with the area, all right? So this is in terms of YCP. If you want to find in terms of XCP, all right, it is negative I XY, all right, sine theta over HCA. All right. So this IXX is the second moment of area because we have first and second. The moment acting in this axis, XX axis, sine theta. So what is theta? Can anyone tell me what is theta? How the theta is measured? From where?
From the x-axis?
Okay. The theta is actually, okay, this is the angle. And then this is the surface. Okay, where is theta? Okay. And then this is the, okay, where is the theta? Let me show you another one. Okay, this is the vertical. Is it this alpha, this beta, or this sigma? I think gamma. Which one is correct?
Gamma.
I think gamma.
Gamma.
Okay, the theta here actually refer to the angle between, is the angle between the plane plus horizontal axis. All right, so this is the plane and this is horizontal. So normally we take this gamma as the angle, all right? So HC is the centroid height. For example, this is centroid. So HC is in this length. This is HC. Okay. So why it is negative? Anyone? Why it is negative? What negative refer to? Anyone would like to try? What's the negative refer to?
The height is going downward, limiting it toward downward.
Yes, correct. This is the displacement. So negative means it is below. Below what? Okay, so this is, for example, this is our centroid. All right. So negative means it is from here. Right. From the centroid below here. This is we call as the YCP. Okay. So this is actually the resultant force, Fr. So can you see here? The negative means it is below the centroid position. Everyone understand? What's the negative means?
Yeah, doctor.
Okay. So can you see here? I have the second moment of area. All right. For example, you have different kind of plane shapes. For example, this is rectangular, this is triangular, this is circular and semicircular. If you deal with this shape, in order to get the IXX, remember, this is our okay. All right. Let me draw here. Okay. This is how to look at the IXX. So I try to focus on this part first. Okay, this one. All right, I hope you can see. So for this case, this is the rectangular plane submerged. All right, submerged rectangular plane. So when we deal with the IXX, means the second moment of area having the moment at XX direction. So can you see XX? This one. So for this case, Ix x is equal to b h cubed over 12. So this is x. Okay. This is x, this is x. So the moment will be in this direction, all right? This is just example, the moment, all right? It tried to bend in the XX direction. So the formula in order to get IXX is equal to BH cubed over 12. So what is B? B is this one. This is BH is the height over 12. All right. So how to differentiate where is B, where is H? All right. For this case, can you see? Okay, for this case, all right. This is IXX. So just plug in the value of B and plug the value of H cubic. Then you will find the answer. Normally this value and this value, you can refer to the table. All right. Okay, I think that's all for today, because this section I'm going to I have covered you the theoretical part, which cover the resultant force as well as the locations of the center of pressure. So far, you have any question, everyone, before we end our session?
I think no, doctor.
Okay, thank
You
you.
know, doctor.
No, doctor.
Okay, so after this, I'm going to share the video recording, and I hope you can revise because it's very important you understand the theory first in order to use your theory and apply to this exam.